All right, so I hope you've been satisfied with your grade. So this is the class average. Out of 30, it was 19.4, which I guess is not bad overall. This is the histogram of the distribution of the numbers. So the majority of you guys having around the grade of 20 to 23, so around 6 or 7 people. So that's the number of people that have been classified under a certain bin, right? Perhaps these are those some zeros that I should have excluded already. That is the histogram per question, so you can say performance. These are the number of students, and these are the questions. So question 1 had 8 points, 2 15 points, 3 10 points, and these lines are the mean. The crosses in the middle, or sometimes upper or lower, are the median. This is called a box plot, and the boxes shows normally from 25% to 75% of the distribution, so they call it whiskers, right? And the outsiders are called outliers, but depending on the way you do the box plot. So these are the outliers. Also, this guy who had 15, so there was, I believe there was one guy who had 15, so it's going to be considered as an outlier as well. But on average, you see that question 3 was like 10 points for everyone, right? Question 2 was like sort of expanding more. On average, it was 6. The median was like 6 point something. Question 1 was also pretty easy, I would say, because the median and the mean were like around 6 out of 8. So I would say question 3 and 8 were super easy. Question 2 was like moderate. So do you have any feedbacks for me? Do you want to say it publicly? If you prefer, you can email me later. But what was the overall feedback?
I just would have liked to know that we needed to do more complex derivatives for the test. I feel like it's not something we necessarily did a lot of in class, and it ended up having a really big impact on the test. So if you could do that, then you could do really well. But if you couldn't, then that whole 15 marks at the test
I see.
is inaccessible. Which doesn't really seem the point of the course, to be able to take derivatives.
I see.
So I feel like it didn't necessarily correlate to my understanding.
I see. It was a pity in this course. I asked the department to assign some hours for lab, but apparently it wasn't the case here. So last semester, when I taught almost a similar course at U of T, we had like I don't know, 3 to 5 hours per week for labs, right? So it would help you guys a lot. And because of that, I had to change a lot of things in the slides to add some more intuitive things for you, just not to be theoretical, right? Because I believe you're taking this course to learn about machine learning and do some hands-on later on. That's why I was, this week when I post the second assignment, you're gonna get your hands dirty on a neural network project, okay? So I believe it's gonna be helpful for your career if you were to work outside as an ML engineer or something. But yeah.
So just expectations of what we should be able to do that we haven't heard in class. I think it's perfectly fine for you to expect us to be able to do that derivative with the gradient, but just saying you guys should be able to do this, or at least if we know to do that kind of stuff.
So the difficulty of the gradients were the issue, or?
For me, I just didn't see it coming.
Oh.
Yeah, just to add on, the questions that we got for practice and that were on the tests were very helpful, but I feel like for question 2 specifically, we didn't have enough practice to go along. I agree with him in that, the gradients are doable, but we didn't have enough practice to really know how to do it.
I see. Has anyone taken a look at the reference books, the deep learning book? So the first and second chapter was almost a recap of linear algebra, and was it helpful?
I only read it for the ML stuff.
I see. Any other feedbacks?
I think maybe having I know other courses will give us practice problems just before, not necessarily even for what's on the test, but just give us more exposure to different types of things.
Mhm.
So maybe having something like that where you can just see other types of questions, even if they're not going to be seen on the midterm, just to kind of get
Right.
aware of like what is the expectation in this field.
Right. Yeah, I understand that. My purpose of this course was you guys learn about the basics of machine learning, and then do assignments. But given the current circumstance, I wasn't able to add. I wasn't having any lab time at all. So what I could do the best was to increase the assignment value. So like your midterm is almost like 30%. For grads is even like lower, right? So I would say don't get discouraged, because given the average of around 20 out of 30, at most you lost 10 points, right, out of your 100. So you're still among because I'm pretty sure you can do well in assignments, and final will be mostly neural net and other things. So don't get discouraged. Normally, since this is my first semester at York, what's the range of midterms here, like out of 100, or undergrad or grad? Do you have any distribution? Almost.
It's pretty average. Like 65 is probably about average.
So it was okay.
I think I don't think any were actually expecting to do as well as they did. Like, I think a lot of us came out of that midterm expecting to do a lot worse.
I see.
And like we were like, well, what was that?
Yeah.
At least specifically for question 2, I think 1 and 3 were like.
I see. Yeah. Okay. At least I'm happy that the outcome was it's okay. The process wasn't. But if you take a look at the solutions, if you read it right now, after a week passed from your midterm, perhaps you're going to realize it wasn't that hard, right? Perhaps you're going to see you could have, perhaps you ran out of time, some of you. Because at first you had a 4th question and I removed it the last minute. So yeah, you kind of got lucky. Yeah. But if any other wanted to just give more, I don't know, anonymously, you can just create an email with whatever ID and send me an email. Do whatever you want to say.
I was going to say about the midterm, I feel like it was a bit too long for the time that we have.
The questions?
No, I feel like it's too long.
I'm pretty sure question 3 and 1 would take combined 10 minutes.
You have to redo.
And you had like 1 hour and 20 minutes for question 2. I'm pretty sure that could be possible, right? Wasn't it the case? Wasn't it the case for question 3?
I feel like question 1
First one was really tedious.
Yeah.
Really? Did any of you run out of? I saw one of you writing me like I ran out of time, and then that was the end of the story. But did you run out of time? Like, say if you had 10 more minutes, would you have done better? So time wasn't the issue then. All right. So, yeah, and your TA is grading currently. He's gonna post the grades sometime soon, so you have a better clue. Do we have it drop that? So we still have time. Okay. I hope nobody drops. Yeah, I'm sure you can do well. So we'll carry on.
Is that 5% or 10%?
The first assignment?
Yeah.
Yeah, it's 5 points. 5 plus
So
1 extra.
5%.
Yeah, 5%. Yeah.
So I'll say 10%.
What is it?
Assignments?
No, the first assignment was 5 grades. So the second and third in total is gonna go up to 30 or 25. I should double check. Yeah, 30. So the second assignment, which I post in a few days, it's gonna be like around 10 to 15 points. So it's gonna be mostly neural network. So I'm pretty sure you can get a good grade on that and compensate your midterm. But to me, midterm wasn't that bad. I'm seeing the average and the performance. Unfortunately, because of those gradients, and I couldn't do more because I didn't have enough time to teach everything. But the gradients, let me just backtrack. What was the prerequisite for this course?
There is
There's none. Like
23rd.
I don't think so. Yeah.
No calculus, no algebra, no statistics, nothing.
We do those like
Probably
3 years earlier, so it's like a lot. It's not fresh. Like we do linear outgoing,
I see.
and then now all in our 4th year classes, they're all expecting us to have like
Ah, I
knowledge
see.
of it, and we're like, what's happening?
Right.
It's been a long time. So we do
Right.
a lot of circuits in 2nd and 3rd year.
Right. I see.
They should definitely make 2310 a prereq, because like, I remember doing ratings and stuff, but
yes.
that wasn't in Calc 2 at all, so a lot of people prereq.
I see.
So I think it's fine, yeah. It's just like expectations. Like if we know to prepare for it, then we'll practice doing grading.
So none of the questions that I posted as samples were close to the second question?
There's one, but it's just like, I don't know.
Yeah, there was one, but it was a bit too simple.
Because I can't recall which.
It was a really simple one.
Oh.
And then this one was like, I don't know. I haven't taken derivative of log in forever. So,
Right, I see.
I don't remember the rule off the top of my head.
Yeah.
And then that to block off like half the marks. We're usually testing.
I see.
Professor, I kind of also noticed this course takes in only Calc 2 as a prerequisite, but I think they should make it Calc 3 as a prerequisite because Calc 2 is only there's only single variable intervals and it's only single variables. But Calc 3 is the one that deals with multivariable. So I think that's also one thing.
Calc 2 isn't a prereq.
Calc 2, but 2030 is prereq.
2030 is a prereq, but we don't use anything from 2030. It's a must.
But the thing is, 2030 needs Calc 2. So technically,
I see. Okay. All right. So let's get it started. Today we're going to talk about the third part of neural nets, which is a backprop. I'll try to just go step by step here and see where we're going to get to. So the two related chapters, if you wanted to have a better reference, is going to be the chapter 6.5 of deep learning book and 5.3 in the Bishop book. Okay, so you can feel free to refer to those chapters if you had any other issues. And of course, just by Googling backprop, I mean, you're going to have tons of materials online. So in the last lecture, we reached to the point that we are able to go feed forward. That means that we are able to compute those intermediate nodes, S of J's of L, using their weights and inputs of the previous layer, right? And then activate those, go back to the next level, up to the point that this is assume this is the last one, so X of J of L. And then using a loss function, we can compute either way with least square methods or other methods. A delta L at this point that we want to back propagate through the network and update all the all the machines backward. Okay, so that this will take one iteration. So one iteration for feed forward, we find the loss function, and then we backprop all those deltas and find what was the specific delta corresponding to each of those elements backward. So in total, one way we go, in one iteration we go forward, we find the error, we backward, so this is one iteration. All right, so inputs were, your input of course has your vector of x, which you input to the model. The output is the y, suppose it's a classification. So the loss function, we call it E of omega. The omega is your model parameters, so all the weights, right? And so finally, the goal is to find the partial of E of the omega, which are the weights, which are the model parameters with respect to assuming those w's as a parameter, right? So we take the derivatives with respect to w's at each point. So this E of omega, as you know, is only dependent on the weight, right? So that's why we have only weights here. We arrive to the point that we can use a chain rule. I'll describe one more example in the next slide. That we can expand the partial of En omega with respect to W's is equivalent to the partial of En, that error we found with respect to the intermediate node, right? So is that if you can just solve these two together, and then we're going to go back to the same formula. So this is the intermediate node. So you can make it in two levels, right? So that's the overall view. So say you are in layer L, all the coming weights from the previous layer have come here. This is the intermediate node for the layer A, layer L, and then you use the activation function, you pass it to the next level. So these are going to get treated as the input for the next layer now. So the next layer has its own WL plus 1, right? And then you can compute using a multiplication, so match mul in TensorFlow. The output of this for the layer L plus 1, so these are the output, and then you activate it, you send it to the next layer. So the last layer, which we call it with capital L, outputs x of n of L, and you can, out of that, you can compute your E and your loss function accordingly. So let's just have questions. And your E is just the comparison between your output, your predicted output, and the actual output. Okay? So let's expand a little bit more on the chain rule. So in algebra calculus, so we have this notion of chain rule that we can expand a d of x, a d of y with respect to d of x, so assuming the x and y are the parameters, as the derivative of the outside function multiply the derivative of inside function. So let's see what that means. If you're dealing with a compound formula, such as this, a very small example. Say your y was 12x plus 2 all raised to 8, right? So certainly, if you want to compute the derivative directly, it wouldn't be that straightforward. So using this notion, you can expand this into a chain rule, right? And then first compute the derivative of the outside function. So what is the outside function here? So this is the outside function. You don't care what's inside, right? So you have to find the derivative of the outside function, and then you multiply it by the derivative of the inside function. The inside function, at this point, you just treat it as 12x plus 2, and you don't care about the exponent here, okay? So that's the way you should go about it, okay? So let's see, if we go for the derivative of the outside function, so it's the power rule, right? So this will become 7, and then you have 8 here as a coefficient, right? So that's your first part. That's your first part. And then the derivative of the inside function with respect to x, right? So if you treat x as the parameter, so it's going to get only 12. 12 only survives outside this. Then finally you can just multiply these two, and then you have 84. Okay? So this is a basic example of the chain rule you can apply, and we use it later on in the backprop.
Professor, why isn't the coefficient supposed to be 8 and then the power 7?
Oh yeah, of course.
Oh, okay.
Yeah, that's a typo. So this should be 7. We update it right now. So 7, 12x plus 2, 7 multiplied by 12. fill this. Okay. The next one also as well. Four. All right. So we take this notion and we use it inside throughout the backprop process. Now, as you knew previously, we assumed that let the partial, the delta J at layer L is going to be equal to the partial En, the error we found with respect to S of J of L, right? So the differences, the update that needs to be done for the intermediate node S that comes back from the next level is dependent to the actual error we found, treating those S of J's only on that specific node as parameter. Okay. And also we knew that the going a step one level further, so from S going backward again, so this is your last layer of L, you found the E, and then you go back to the delta, you reach Sj. So the Sj at this point, you only care about the En you found and the Sj itself, right, as one module. And then if you find the deltas here for that, you're going to go back here, go back, what else you have? You have W's and the X's, right? You just need to compute this again. If you add multiple layers, you're just going to come again here, another Sj minus 1, and then you're going to update it here. Then you go back, you update it here, and you go forward. You see, step by step, you backprop throughout the network. So we call this partial Sj of L with respect to W's as X of I of L minus 1, the input of the previous layer. Okay. So, and we knew previously that Sj, the node Sj at layer L, can be computed as the summation of all the W's and the inputs it has. The inputs of the previous layer that are input to that specific layer with that weight that we already had. Okay. So finally, if you're going to combine these two, so the partial En of omega divided by partial W is going to be Xi multiply delta. And we were asking how we're going to find this delta, right? So that was a job of the backprop, and that we're going to see that it's another chain rule for itself. Okay? All right. So let's recap again our E of omega, right? Say at intermediate node J, which has S of J of L, only depends on the W of that layer, right? So if you want to expand this to the partial E of omega divided by partial W's, it's going to be, again, another recap. E with respect to Sj, and then Sj is also depends on W, right? So that's the second expansion. So using this chain rule, derivative of the outside function multiplied by the derivative of the inside function, you're going to have this, and a derivative of that is xi L minus 1, right? Let's combine these two in the next slide and see what we're going to get out of this. Okay? Up until here, everything is clear? All right, so if you combine the two, you're going to have the derivative of E with respect to W's at layer L is going to be the inputs of the previous layer, L minus 1, to that layer, multiply the delta, the updates that we need to be done at layer L. Okay? And that was sort of an expansion in the vector space. So the x vector can be represented as this. The delta of L can be represented as delta 1 of L up to delta D of L. So it is just another form of representation. So finally, this is just like this in vector. Right? It's a vector product or a matrix product. That's why you have this transpose here. Okay? And now we have to use chain rule again to find the delta L here. So how are we going to compute this? We're going to see next slide with a simplified case. Just don't get confused between these two. This is the partial, this is the D, and this is delta, right? These are the updates you found. You can just write it D as well if you prefer. Sometimes they write it this way, delta. All right. So let's consider a simplified case where we have only one hidden layer, okay, for simplicity. So that means that we don't have this S of L, right? So in one step, and consider we are using the least square for linear regression, okay, as a loss function. So it's a mean square error. So that means that this one, with one level, is going to go back, it's going to activate, so that the theta will activate the output of the S of L, which was a matrix multiply of its weight and input, and then you're going to have the output, okay? So that's your G, your final output. The function that you use to mimic the unknown function of that problem, okay? You compare these two, your X of L, which was your predicted output, and the real output, and you find your E of N with respect to the omega, which was the weights used in this way. Okay? Now, the delta at this point coming back is going to be computed pretty easy because it's just one chain rule, right? So the D of En with respect to SL, so sitting here, looking this way, so the error you got here was dependent on this node, right? So this node is the parameter. You need to change it using the delta you found, right? So this is equal to the En of partial SL, and you can expand the chain rule here. This itself corresponds only to this, the first node, and the first node corresponds to this, the second one. Okay, that's the chain of these two. A two-step. So the first term, this d of En of omega divided by partial of d. Since we were using millis square, so this 2 will come out. You're going to have 2 multiply x of L, which was the output, minus yn, the true label. Okay? We knew that the output of xl, let's get rid of this. This is the activation of this, right? So we multiply the weight and the input. We're going to come back to the output here. And then we activate it, right? Through an activation function. It was sigmoid or hyperbolic tangent or whatever. Just we activate it. We activate the output of this. So this was equal to this, right? So then, if you want to compute the second term here in a chain rule, the partial XL over partial SL is going to be the, of course, the theta prime of S of L, right? If you recall, in the sigmoid and hyperbolic tangent, we mentioned that we need to have a lot of derivation of those. That's why we picked the specific activation, because this term can be easily computed by 1 minus delta square again, right? Because that was a hyperbolic tangent. So that's why you understand here now. It's going to help us make the process more efficient. So just think about this for 1,000 and thousands of times. Every iteration you need to compute so many derivations. So this will make it easier to avoid so many unnecessary computation. So we have found the first term here and a second term. So the output, so the delta part at this point, it's going to be this multiply this. Is it clear up to now? All right, so now we found how we're going to update the first layer before the last one, like this one, the penultimate, say, layer. And so we are considering a simplified network with mean sort of a regression like error, okay? So now let's see how we're going to update, so using this that we found, how we're going to update an intermediate node before this. Okay, so we are only reaching up to this step. So we found, so it's up to here, right? That was the XL and the output. We backprop for one step, and we are arriving at this point. Now we're going to have this delta, and we want to update this. Okay, how are we going to update these weights? Okay, assuming that they are available, assuming that the partial En with respect to Sj for all the j's from 1 to d, right, are available. Okay. So let's see how we're gonna update this node. So I put the figurine on top right. So the chain rule was telling us that partial En over partial S is going to be partial En over X's multiply those partial X's over X S of I at layer L. Okay. So this term, we already computed this. So it's going to be the theta prime of S of I. Okay. So we need to compute this now. Another chain rule for itself now. So we computed the second term. For the first term, we need to have another chain rule of its own. So this will compute it here. So the partial En with respect to those x's at layer L is going to be equal to all those different inputs, right, that were coming to that specific layer L, which are from 1 to L plus 1, right? So we have the sum of j's from 1 up to d of L plus 1, all the partial En of S of j, L plus 1, this is plus 1, multiply partial S of j divided by partial X of I, okay? So, can somebody tell me what this means here? So, you recall we had previously this. So this is actually the summation of all the deltas multiplied by W's, right? Is it clear why? So in order to compute the first term, to understand what are the actual updates with respect to x's that coming through that layer, so we need to actually multiply the delta we found on the next layer by the w's of that specific layer. Can you visualize this? So you found the update here, perhaps outside, and then you found your backprop it up to here, and then given this update, you want to update this intermediate node, so the W's, right? And then it has this update will go back again if you have another input. It's gonna update it here. So 1 step, 2 step, and 3 step. So we are in the second step. I'll wait. I'll pause here for a second. So, is it clear up until this point? We discussed it in the previous slide, right? So, you remember we had this. So, the last layer, you apply the chain rule, partial En divided by partial S, right? So, you had to compute two terms, this one and this one. This one was the actual mean square error, right? So that was the derivative of this. So 2 was coming out, the power. So 2 multiply xl minus yn. So and then multiply the partial xl of sl. So we found it this way. The derivative was theta prime. And that was actually this. Okay. So coming back, so we reach up to this point. Now we go back, we want to update an intermediate layer using the delta we found here. Okay? So this. So now set the layer as this. This is coming from the layer after, right? So the delta L plus 1. So you apply the chain rule again for this term. And it's going to be equal to the delta you found backprop from the next layer multiplied by the weights you can compute in order to find the partial En of omega divided by partial x of I of L. So if you put this together, so you actually, your delta I of L, so that the update you need to be doing at layer L is equal to the multiplication of the delta J of L plus 1, so then for the next layer, multiply by the W's, you multiply the output, so it's a point-wise multiplication of the theta prime of Si. So you can show it in vector notion, so this is a vector format, right? This is a point-wise multiplication, so circle and cross. So in order to find the vector of delta, you need to compute the weights multiply delta of the next subsequent layer, right? L plus 1, a point-wise multiplication to the theta prime of SL. And that's actually the essence of a backprop. So at each layer, in order to compute the update, you need to have these matrix multiplication multiply a point-wise multiplication here. So that's the overall computation that neural net is dealing with at each iteration. Okay. So just you have to put this in a for loop for every node and the number of layers you have. You have to compute this one by one, and that's going to be one forward pass and one backward pass. So it's one iteration. So say you want to update your network, you want to train it for like 1,000 times, 10,000 times, 10,000 times. This should be going on and on. So you can understand easily that why in the late 80s and 90s, because the math was there already, but nobody was able to deploy big models because the computation part was not there. There were no GPUs, right? It was only a single core CPUs, and it would take like 6 months to train a huge network. That's why nobody was interested in investing in the field. As soon as the GPUs came out, the parallel computing was more prominent. You had multi-cores, many cores, now FPGAs, supercomputers. So after 2010, so suddenly it exploded. So people saw that, oh, these computations can be done efficiently now. You can just parallelize it, right? Now you can train a model at state-of-the-art CNN in less than 3 hours with your own GPU. So that made a huge difference. Okay. So these are the definition of the matrix of W. So from W11 of L plus 1 up to WD1 D plus 1. Okay. All of them are in R space DL and DL plus 1. And that's the vector definition of a theta prime. Okay. So let's put all of them together in one unified algorithm. So your input for a backprop algorithm is, of course, your inputs and your omega, which are your weights at the current state, right? You're at iteration 1255, so these are your weights. That's your omega. You have passed some inputs. You've done the feed forward, and you have computed as an output this for the last layer, so you want to backprop it throughout the layers from 1 up to L, from L to 1. Okay, so the first step is obviously do the forward path. You want to compute each of those S of L and X of L's, right? Every intermediate node, which is the output, and also the output, which is X of L, for all the layers, right? Because the computed S of L is going to be the input for the next layer L plus 1. So you have to do this for all the layers up to reach to the last one, which is X of L, capital L. And then you can compute the loss function with whatever mean you were defined to do that. Absolute way, least square, mean square, error, or any other technique. Then you have to, for the backprop, you have to come and compute the vector of, or the matrix of delta, the partials of L, which is the derivative of this pointwise by theta prime S of L. So this is the gradient, and this X is, you treat the X's at this point as parameters, right? So the gradient with respect to X of L, your G. So this is the first step. Then you come back for all the intermediate. So that was the first slide you saw for the simplified case. That was the first slide. And these are for all the intermediate nodes. So for all the L minus 1 to 1, so 1, not the L capital because that was this. So this is for L. For all the rest, you have to update this. The delta of L is going to be the theta prime of S, pointwise, the W, and the delta. Right? And you just make it in a loop up until to reach you reach the first layer. Okay? Does that make sense?
Sorry, was that not intermediate?
Nodes.
Node?
Yeah. All right, so now you know in high level how we can compute backprop. I would, again, since we don't have any lab time, I would urge you guys, all of them, to have a look at this. This is very small, so it's going to take you like perhaps 2 hours to run through this. I'm sure you have by now, all of you have installed TensorFlow because it's just, have you done that? So please do that. See the manuals that I put on Moodle, so because we're going to use the second assignment with TensorFlow. If you're using a specific version of Windows or Linux, it's pretty easy. You can just download the pre-built library. You don't have to compile it from source code, right? Just 2 lines. You can find it in TensorFlow website. So install the library, and then all you have to do is just your import that library, right? So take a look at this post. It's going to replicate whatever I mentioned in this slide, in this lecture, from scratch. So it's going to build a backprop from scratch using TensorFlow. And then you can have a look as a TensorFlow built-in automatic differentiation. So when you use these 2 lines, so tf.train gradient descent optimizer with the learning rate and dot minimize cost is as if you're asking TensorFlow to do an stochastic gradient descent, 1 backprop, and 1 update throughout your network after you initialize your network. So all of these a few pages will be summarized in these 2 lines that TensorFlow does automatically. So please do that. Have a look at this up to Wednesday. And Wednesday, after we finish the 4th part of neural network, at night I'm going to post the second assignment. You're going to play around with neural network and train them a little bit and tune with the hyperparameter. Yeah.
Will this have
At first, I wanted to ask you to do something similar, but I'd rather not to, because I'd rather to just give you some more practical examples rather than just implementation. Okay? Yeah. Question? All good? All right. So please take some time and install TensorFlow and have a look at this. You'll understand how the process works, and then on Wednesday, when we finish neural net, you're going to be able to start working on your second assignment. Right. Have a good day, guys.